very fast. So most people thought you could never see a neutron star, but the circumstances do arise where you can see neutron stars. So they could measure the mass, usually because they were in binary stars, and so you got neutron stars. So, but then in 1970, Stephen Hawking sort of came and described a lot more about black holes. That's why he's very famous. And then finally in 1970, Cygnus X1 was discovered. All that means is that it's the first X-ray source in the constellation Cygnus. Except it sounds a lot better to say Cygnus X1. And the way it was discovered was that it orbits, it's a part of a binary star system. It has a very massive companion, and the massive companion is orbiting nothing.
Binary star system means what?
It means two stars. Binary star systems has two stars. So there's a large companion, and in this case, the way they could see it was emitting X-rays, but no optical light. So in fact, if you looked at this system, you saw one star orbiting something, but there was nothing there. And then when they looked at it in X-rays, they saw X-rays, but it wasn't, the X-rays weren't coming from the big star, it was coming from there. And this was when they discovered the idea that, hey, maybe black holes aren't sort of black. I mean, they're black when they don't let the light escape, but when you drop something into a gravity field, say you drop a ball, or you fall off a tall building, the higher the building, the bigger the impact. Same here, as the gas goes from one source and falls onto the black hole. Now, there's no surface to the black hole, but as it starts spiraling in, it gets hotter and hotter just by friction. And so that makes it emit a lot of light, and it gets so hot that it starts emitting X-rays. So there was a way now to finally get a sense of what a black hole was, where the black hole might be. But that was still, the very beginning of it. Now, there's another mystery to talk about here. And this one was way outside our galaxy. Well, first of all, it even started before the idea of galaxies. There used to be these things called spiral nebulae. They didn't know what it was. Nobody knew how big the universe was. And all they thought was that these were nearby gas clouds. And there was a guy in Lick Observatory in San Jose named Fath who noted that the nebula was, some of these nebulae were actually emitting a lot more light than they would expect. And the light comes out, basically this is what it should be like. This is a spectrum. All that it is it's a measure of light at different wavelengths. It's the rainbow. The blue side is over here, the red side is over here, and a normal galaxy is just basically a lot of squiggly lines. That is, there's some absorption, but there's some amount of light. What he was noticing is there were big spikes in some of these nebulae. He didn't know what it was. They didn't even know what a galaxy was, which was that it was about 100 billion stars and way outside our galaxy of 100 billion stars. So, and then by 1943, Carl Seifert comes along and says, hey, there's a whole bunch of these guys. So he creates a class for them. A whole class of objects, and they became known as Seifert galaxies. Now notice that nobody's even thinking black holes now. Black holes are having their own controversy. Nothing relates any of this to each other at this point. And then they start looking into radio waves. And there's a whole bunch of radio galaxies, galaxies that are emitting radio. Okay, what are those? Why are they emitting radio waves? People didn't know. They tried to look for what was going on, and they found these other sources which were emitting radio waves but were star-like. And they called them quasi-stellar radio sources because stars don't emit that much of the radio. Another mystery, not clear, but these objects were very far away. That's all that they could tell about them. So finally we come to this part of it, to Mount Aragats. This is a picture that I took when we went to Armenia a few years ago. That's Mount Aragats over there. It's supposed to have 4 peaks. Actually, it doesn't have 4 peaks. It's a volcano that the caldera collapsed. So all that it is that's where it used to erupt. And in 1946, Victor Humboldt-Zungian, who was already a well-known astronomer, basically said there should be an astrophysical observatory in Armenia, and he chose the steppes of Mount Aragats to establish the observatory. In 1958, he'd already started thinking about these things called active galactic nuclei. So there are these galaxies that are emitting more light. Nobody knows exactly why they're emitting more light. And so he's thinking of this and he says, not only, what if there's a large amount of material that's coming out? There's huge explosions at the cores of these galaxies, and then most likely there should be huge masses at the cores of these galaxies of an unknown nature, is what he said. Now, here's an interesting exchange between Walter Baade, who a very famous American astronomer. He went up to Martsumian afterwards. He says, "Professor Martsumian, you have come from the Soviet Union and I from America. Logically speaking, you should be a materialist and I should be an idealist. But what you just said is nothing other than pure idealism. It's fantastic. You speak about some kind of non-stellar objects which no one has seen, so it must be something inexplicable, mysterious." That's what it was. So, in the 60s, a Martsumian student, Benjamin Markarian, started a survey of all these nebulae, looking to see which ones had a lot of extra blue, a lot of extra ultraviolet light. With this telescope, this is the 1-meter telescope at Byurakan. That's all right. And again, notice that the reason why they're looking for blue light is there's all this, on the blue side, there's all this excess light that comes out on the blue side. So it's instead of taking the spectrum, it's a really cheap way of finding things that are very energetic. So they started doing that survey, and they found about 1,500 sources. And then Edward Khachikyan brought the catalog to the US as a part of a US-USSR exchange program. And he joins up with Dan Weidman, who was at the University of Texas, and they start observing these guys, and they all look like Seyfert galaxies. So suddenly, and they increase the number of these Seyfert galaxies, these ones that are doing all this excess energy generation at their centers, by tenfold. And from 1969 to 1974, Khachikyan and Weidman published a whole bunch of papers describing all of the new discoveries, and they even reclassified them into 2 separate classes, Seyfert 1s and Seyfert 2s. So what do we have until the 70s? There's a large number of galaxies that have radio emission, large numbers of these quasars that are very far, very luminous, but look like stars, large numbers of nearby galaxies, these Seyfert galaxies from the Markarian Catalog, lots of excess energy. And it was noticed also that these quasars were very variable and on very short time scales. So what was the explanation for all of this stuff? And that's when people said, aha, star formation. We're not going to go to black holes yet. Because if you have a lot of stars, that's a lot of emission, especially young stars. Young stars are blue, provide a lot of ultraviolet light. And the problem was, first of all, you have to group a lot of them together. We're talking about tens of thousands of these stars packed in a very tight area to give you the kind of luminosity people were observing. And then, if they're varying, you can't get tens of thousands of stars to vary in unison. They're just going to average out. And if you pack any more stars together, they're just going to gravitationally either collapse and just stick together or just shoot each other off. And young stars are the most luminous ones, but they have very short lifetimes. They die real fast. So this was the explanation. After all of this stuff, black holes. Why black holes? Because there was no other explanation left. It was truly the last idea. Everybody tried everything else. How could you make these galaxies, the cores of these galaxies, emit tons and tons of light? Well, same as the idea for Cygnus X1. You have a very massive black hole. Material streams into it, becomes very, very hot, and starts emitting an enormous amount of radiation all the way out to the X-rays. How do you get it to emit radio waves? It has a magnetic field. It channels all of this material out, and that creates what are objects like this. You see this stream coming out of here? This is the galaxy, but this is even bigger than the galaxy. It's all the material that's being ejected by the black hole from its center. And this is something, remember, that you can't see it. The black hole itself is not emitting any light, but it's causing all this enormous havoc all around it. And here are some more radio images of different kinds of the radio emission that comes up. It's all of these jets of material that are being thrown out from the black hole. This one is interesting because clearly there's another wind of some sort coming from other galaxies, so it's pushing back its jet. So why study black holes? Why are they important? Why would they be, you can't see them, but clearly they affect the environment that they're in. Also, they create a lot of radiation and energy. How important is that? And quasars, which are basically incredibly luminous, Black holes with all this material streaming in, the reason they look like stars isn't because they're stars, it's because they outshine their host galaxy.